hope that you could able to follow these pictures. There's nothing to discuss much on that, but you have to add some of the inputs so that you can feel that things explicitly seen on the pictures, like the projection, and then you have the peak positions, time taken, then the combination of this can also be done. So these things you can do it. The problem what I have given now for the value-added courses like this, that can also be done. There you have projected the basketball, and then you can trace at different time. This is y of m, this is x of m. That's the same graph which I have shown. So these inputs can be added there and show initially at the height of 2 meters, it becomes 3 meters, and then 2 different times it reaches the time of height of 3 meters, and then maximum is more than 3 meters. All information at different times, which can be shown explicitly on the picture just by adding these information on those figures. Okay, so that will be nice to see, and that can also be explained, and that can animated also with the numbers. Okay, this I close it. We are going to start now the lesson, which is going to be, yes, we're going to start this. Okay, 2-dimensional polar coordinates. I think so far whatever we have discussed is the we have seen 1 dimensions and little bit on 2 dimensions. Okay, and then the different kind of forces that are acting on objects, and if we have the 2 dimensions, so then we can have the possibility of, you can have an x and y, which we have done for the projectile, but here it is going to be in a polar coordinates. And we are going to see that this position vector what you have can be represented by an r vector, and its modulus is given by modulus of r. This is what your modulus, and phi is the angle made by this. 1 minute. By that position vector. Now. Okay, this is the angle made by this position vector, right? So now it can find out what is the x component and y component, which is something like, when you have a projectile motion, velocity has x component, y component. There is a vector, v vector is the vector. Here it is the position vector, which has a x component and y component. So vector concept is equally applicable, where see one places we have used this as a x component of velocity and y component of velocity. Here you are using it for a position. Okay, so now the position vector, which is varying when you move in the direction of r and in the direction of phi. So we'll see that how this we are going to handle now. And we can write it x in this way, and there is a connection between this to this. You can see that r is x square plus y square square root. Phi is the arc tan y by x, which we have seen that you can find out the theta or a phi by using this x and y. And then you have a r vector, which is equal to magnitude times r cap. That is the direction of the r vector. Where this is a cap here. You can see there's a cap. This is a unit vector along the direction of r, which converts the multiplying factor r into a vector because of this unit vector product. So this is within the vector quantity, and of course we know how to write how to find the unit vector for a given vector. Just take a vector divided with the modulus, which is the cap. So this is the connection between the polar coordinates, polar variables r and phi to the x and y. This is the relation which we have found. This is the definition of the polar coordinates. Now you can see, look at what is happening x and y. This is the x cap, and when you are moving along this, there's an r cap and a phi cap. You can see this is 90 degree with respect to this x and y. This r cap and phi cap also 90 degree. Okay, so this 90 degree is something which we have to follow, that nobody can question this one. Why not have 120 degree as a base? Well, you can do it, but your system becomes very complicated to handle it. Doesn't mean that it cannot be done. It is so convenient to handle. So these are all orthogonal.
വിശപ്പുണ്ട് തോന്നിയത്.
This is a orthogonal quantities. There's an orthogonal angle here, 90 degree, 90 degree. This is also 90 degree. Okay, now you can see there is a unit vector along the x direction is represented this. And this is the r cap along the r direction. Not only dot product, there are several things that enters of the 90 degree. References, reference mutually perpendicular axis are a sort of mathematical elegance for us, and things can be simplified very easily. Does not mean that we cannot solve the vector in terms of 180 degree base. We can do it also, but 90 degree is more convenient. For example, you know, in a hexagonal system in a crystal, HCP, right? You define in terms of the position vector in terms of 120 degree. You will get two vectors, no? So this also possible to do it, but this will be, this 90 degree business helps to resolve them easily. See, when it comes to 90 degree here, this cos pi and sin phi, they are perpendicular automatically with respect to the phi value. So when it goes and sits on this y axis, it's 90 degree. That's the phi. Then you can go back, and this will be get connected to your exponential, you know, e power I. Okay, that's also linked to that. So therefore, several things very, very convenient, okay, to handle the mathematics. So we'll assume, we'll accept that as it is, but there is a way to handle them other than 90 degree also. Okay, so that can also be done, but this will, we will realize that this is much more convenient. And you can see here how, what is the explanation for this. The unit vector sk points the direction of increasing x with a y fixed. This is fixed. This is increasing x. That's what is the meaning of this. The unit vector x points in the direction of the increasing x with a y fixed. Unit vector r cap points in the direction of r with phi fixed. See, you can see what we are fixing here. X is, y is fixed here. This is pi is fixed. And pi cap points in the direction of increasing pi. This is the increasing pi. It goes around. So pi cap points the direction of increasing pi with a r fixed. So that's how the direction goes. Unlike x cap, the unit vectors r cap and pi cap changes as the position vector r moves. This is important statement. Unless or unlike x cap and y cap, the vectors r cap and pi cap changes. Unit vector changes as the position vector r moves. Okay, when the position vector moves, you can see the vectors r cap changes as the position vector r moves. Whereas here, suppose the position vector is changing. I don't think we have any change in the x cap and y cap. Suppose in the same direction you are moving, correct? So you don't see any change in the x cap and the y cap. Okay, that's important point. Whereas the position vector here, if it is, you can see pi cap points the direction of increasing pi. This is increasing pi. For example, somewhere about 30-40 degree, it goes to 90. It is increasing direction. Increasing pi with the r fixed. Unlike x cap, the vectors are, both the unit vectors changes the position, change as the position vector r moves. When it is moving, this is changing. This is changing, whereas they don't change. Okay, when you are moving like this direction, this cap, x cap and y cap is fixed wherever you are. You simply go on, but the direction of this and this are fixed. So that's one important change that is going to take place with respect to this polar coordinates, where you have an r cap and pi cap with the unit vectors. Which means you can see that x cap and y cap will be always perpendicular. Which means here also they should be perpendicular. So which means by just finding a unit vector, take a dot product and you can confirm it. Thus, you If it goes to the dot product goes to 0, which implies that 90 degrees is observed for both pi cap and r cap. Okay, that's quite natural to see. So now we can see this unit vectors in plane polar coordinates. What is this unit vectors r cap, pi cap, and how we are going to find out with respect to this axis? When this is sitting here, what could be the connection to this x and y, or x cap to y cap to the r cap to pi cap? That is what our relation which we are interested. Now we look at this one. We take a unit vector in which the radius vector is going around, which means theta is changing, or a pi or a theta, doesn't matter. Some text they will use pi, some text they will use the theta, but pi will be more meaningful because theta, when you go to spherical coordinates, theta will be with respect to the z axis. Pi will be in the plane, and cylinder also pi will become mostly used, but there are texts they follow theta or a pi, interchangeable, doesn't matter. Okay, now let us look at this vector here. It is moving straight. Okay, then now I wanted to find out what is the unit vector here. Okay, it has a components with respect to x and y. You can see this an x component or y component connecting a unit vector r. Okay, you see r has x cap and y cap. One of them is the cos theta, other one is the sin theta. That is what your unit vector is. Similarly, for a theta cap, you find minus sin theta x cap plus cos theta y cap. So now we can see that this is going to be a minus theta is a x component. That can be understandable very quickly by looking at this one. Okay, you can see this theta, and this is going to be a minus direction. Therefore, minus sin theta is this, or this vector. Is it not? Are you able to see that? This angle and this angle are equal, and this component for the e theta. See, what we have resolved for r is this is the cos and this is the sine. And then when you come to this angle equal to this angle, therefore you find this is going to be a minus sin theta x cap, which is opposite to the x direction. Okay, this theta component what we have, and this is going to be a cos theta. Clear? I think this you have to.
Yes, sir. Yes, sir.
That we are going to see that. When theta changes, what is going to happen? That's what our. Now you can see this when theta changes, this r cap is changing. Which means we will just go through this some more details and we'll come back. Okay, for clarification. So now I have two vectors which has been resolved for this position vector along the direction of r cap and theta plane. So some text you can see they will use ER and E theta. Some places they will use R cap and theta cap. So these are all unavoidable, and text depending on the textbooks we are going to see, they will be using. It doesn't matter for us. Okay. So E suffix R is in this direction. E theta is along this direction. This angle is 90 degree, and with respect to this axis, this is going to be theta. That's what this theta. Okay, this is understandable. This is easy for you to find out. And you can put this sin theta, cos theta, sin theta, minus sin theta, cos theta in a matrix form also. Okay, you can put this is a matrix and multiply with the x cap and y cap column. You will get this result. Okay, this is sort of a rotation matrix. I can put it like this: cos theta, sin theta, minus sin theta, cos theta, and then a column vector x cap and y cap. If you multiply, I'll get this r cap and theta cap. Okay. So now I'm making a plot of x and y in a vector field. You can see this is the stream plot or a vector field plot, x and y, and x is varying like this. Stream points are 10 points I have taken. You can have any number of points. Okay, this is blue and thick line which I made it, and then the large stream scale I have to make it a little large. So this is what the fields that are around now. Now, this field can go wrong. Okay, that is possible to have a stream plot of minus y comma x. You can see this has been pushed it to this So what does it mean? You have an r cap and a theta cap. You have a column vector x comma y. You find out what is the x cap and y cap, here x cap and y cap, in terms of r cap and theta cap, that happens to be minus y comma x. I think you are able to understand what I'm trying to explain. You have this equation now. This is a matrix, the column is there. Take an inverse of that and go back to that. When you find out this, you will get this side, x is a minus y component and other one is the x component. And if I make a plot, this is going around. Okay. Let's come now. Yeah, that's what we are coming. That's what the challenge is now. We should, how the rotation comes. That's what interesting. This can be understandable now. So now you can see I just made this mathematically just minus y and x, which is coming out, and that is what is. You combine these two. Okay. This is whatever is coming out radially. I just made one unit vector of that arrow. Okay, and then combine this with the circular part. You can see there's going to be a vector which is tangential at every point of this circle. This vector which is going around is tangential to every point of this vector, which is a position vector. You're able to feel it now. Every point it is going to be tangential. Okay. This is tangential. You make a vector small size, then you can see that. You can feel it. This at this point there's a tangential. We just go around of this vector all the time it will be tangential to this. So you can see that naturally that rotational field that you can get it by putting in terms of vector. This is this vector which is moving around, and there is a tangential vector which is also available for you. Okay, another tangential vector which is here. So now you can put it in terms of a simple problem where you would like to know how does this really cos, same thing here, cos becoming sine, sine becoming cos. That's what the thing that happened. And the derivative of d r cap by dt is equal to pi dot pi cap. This is your pi cap. Okay. Similarly, take a pi cap derivative. Again, you find there's going to be a pi dot and with a minus sign with an r cap. That's also happening, which means you find that pi is varying with the time, or pi cap and theta cap, r cap and pi cap are functions of time. Pi cap and r cap are functions of time. Unit vectors are function of time. That is the difference which makes completely different kind of a dynamics in during the rotation. Is that clear for all of you now? Now you can ask some questions for a clarification. This is naturally happens because by vectors you can really feel that this is the vector which is going to make a rotation when r is fixed. Even though the magnitude of r is fixed, but when it is moving around, you find there's going to be a change in the direction of both the r cap and the pi cap. That is the point. Because you can see r is fixed, magnitude of r is fixed, but when you move it little bit, pi is also changing, r is also changing because the r direction has been shifted. So therefore, you have a r cap is a function of time, pi cap is also a function of time. Therefore, we take a derivative. When you take a derivative of this unit vector, this is the relation connecting this dr cap, which means r cap dot is connected to pi dot pi cap. Now the pi cap dot is connected to the minus pi dot r cap. That is what which is going to happen. That should be used consistently. If you use that, then you will be successful in understanding many things. Okay. So now, is it possible for us to feel that, or is it possible to understand that pi cap and r cap must be written as a function of time? Class, because I'm in the class. Okay. Okay. So you could find it now? Does it make sense now? Then
Yes.
okay. The point is understand that r cap and pi cap is a function of time. That's the most important thing. Once you have that, you write it r cap of t and pi cap of t. Then naturally this is what the relation which is connecting it. Now you can see that r cap dot, which is a time derivative, is equal to pi dot, which is d pi by dt. Okay, this is what your velocity, which is we call it as an angular velocity, right? And it has a direction. It has a direction which is connected to the derivative of the unit vector, position vector. That is the point. And here you see the angle you have d pi by dt, which means pi cap dot is connected to the minus of pi dot, which is similar to this with an r cap. That's the beauty here. Okay. And you can see that the remaining part, what you can write here is going to be minus r cap. So therefore, it's going to be minus pi dot r cap. And here it is pi dot pi cap. Okay. That's because of the derivative component of this r cap, which is a function of t. Here is also a function of t. Okay. So therefore, position vector happens to be function of time. Therefore, this kind of a equation that we are ended up. And also you can feel it now. This is the position vector which is moving around. When this is moving around, which means it's r is a function of time. R vector is a function of time, implies that even though the magnitude is fixed, okay, but when it is moving around, I find that it's going to be an r cap and theta cap that will change it. r cap and theta cap changes, but magnitude of r vector is same. You can see this magnitude is fixed, but direction changes every moment as a function of time. Therefore, this makes sense, and you keep this in your equation of motions and try to look at things. Then you will get a complete dynamics about the polar coordinates. Okay, whereas x cap is not a function of time. I don't have to write x cap of t, y cap of t. That can be checked with respect to these interrelations. Okay, wherever this theta cap r cap is there, the directions will be x cap y direction is not varying with the time. That you can confirm it. Okay, this is independent of time, whereas this fellows, when the position vector moves, they are varying. Therefore, you have to take into consideration of this. It's time dependent of the r cap and the theta cap. Okay. So with this, we try to look at things and see what are the things that's possible for us to understand. Let's try to find out. Let me take this is a matrix form. Cos pi sin pi minus sin pi cos pi. That is what the relation which we have already formed for this. Okay, this is what our relation. I'm taking the pi or theta component alone that I'm representing in the form of a matrix. Find the inverse of that. Okay, I'll get this cos pi minus sin pi and cos pi. Now transpose them, and inverse and transpose are equal. And if this happens, then we can call this matrix is orthogonal matrix. Inverse equal to transpose is the orthogonal matrix. Now, you can see that orthogonal matrix has been proved here by taking inverse of m, that's equal to transpose, is satisfying. So therefore, you can say that this matrix are orthogonal matrix, or in terms of vector, they are orthogonal vectors. Okay, this is the matrix form which we have. Now you take a inverse with respect to this r cap and a phi cap. This is what the relation that you have, and you can find out what is the matrix form also it can be represented. So whatever the relation which you have, it can also be considered in terms of the matrix of this form, and then take an inverse and play with that and just write it down in the form of a matrix form also. That gives the same results as what we are trying to look at here. By having this kind of relations, what has been found can also be found through the matrices. So there's a very strong connection to the matrix and the vectors when you make a rotation with respect to these axes, position vector and zero. Same thing is true with the 3-dimension also. So when we look at in the spherical polar coordinates or the spherical coordinate system, we will look at the including z component, we can look at it. And there are representation of how this position vectors are the so-called unit vectors of this position vector and unit vectors of the pi. How do they change? That can be looked at it by carefully with this kind of a pictures that has been given in various textbooks in various forms, but all merges finally to the results whatever we have already seen with respect to this. Most importantly, you take a time dependence of r cap and pi cap, automatically you would end up with all the results that whatever which we need. Look at this now. I have a theta, and theta is varied by small amount d theta. Okay, and this is the direction of ER, and this is ER which is moved to, this is the, you can see unit vector, unit vector. This unit vector have moved to from here to here. This is a change in the DER. With respect to this, ER1 has shifted to ER2. This unit vector.
So can we tell the change in the position from one?
Now we can look at it in terms of the, it's also true, no? It is multiplied with the magnitude, no?
Yes.
Multiplied with this magnitude. Correct?
Mm.
See, when you describe this, you just multiply with the scalar factor, you'll get this. Okay, so now we have theta and d theta for this. So you do this one, I have a ER1 which is shifted to ER2. There is change in the DER. And what is the DER? Is the change in vector from position here to here. That is DER. Is it not? Unit vector direction has been shifted to from here to here. That is what the DER is. Similarly, you have E theta 1, E theta 2, which is moved by DE theta. Right? Please note that we are looking at in terms of the unit vectors which are get shifted from position 1 to position 2. There is a change in the vector which is equal to DE theta that has been found. Now dr equal to d theta e theta and d theta equal to minus d by der. This is what which we have shown here by taking derivative. Correct? I hope that's right, what I'm trying to describe here. Right? Okay. And if it is similar to this, is it not? You take a vector position and take a time derivative of that, you will get both the results, whatever which we have. Now divide by dt now on both sides. You get it or not? That's what we are required. You know the DER change in what? Unit vectors along the r direction, change in the unit vectors along the theta direction. And divide both of them by dt, you will get the resolution what we have found, which implies that these are ER and E theta are functions of the theta, which we don't want to try like this explicitly, but it comes out naturally by looking at the position vectors. This is the position vector along this ER direction. This is also position along the ER direction after making a small displacement of DER over a time interval of dt. If we take it, then the DER by theta will get it, and the DE theta by dt will get it. That if I do it on both the sides, whatever which I have given, I will be getting it. R cap and pi cap here, and we can see here in terms of what is that? E theta and ER. Okay, with the minus sign. And what is the minus sign? Why do you have a minus sign here? In terms of vectors, how do you look at the minus sign? Well, this must be E theta must be opposite to ER. Will that happen now somewhere? E theta or del ER. Okay, this should be opposite direction. That should be this d theta. Okay, and that's right. You can see this vector and this vector, they are opposite, is it not? You follow? ER vector and d theta are change in the d vector. These vectors are opposite direction, therefore there's a minus sign. That's how they are introduced minus sign, which is naturally we are getting it by taking the component differentiation as a function of time when you take it. Here they I know that directions is opposite. I hope there will be something which can give you the clear picture about dr and d theta. So the del E theta and ER, they are opposite direction. Therefore, you can have a minus sign. That makes sense. Okay. E2 theta minus E theta 1 dE theta. Then dr, this is what you have. This should be shown, and when you are showing that, you should be in a position to understand that dr can be written as d theta E theta. It is something like you have an arc length, no? D theta is the arc length, d theta into ER. Okay, this is the radius. So same thing here, we are using it here also. So arc length that should be taken properly. And when you do that one of them will be opposite to the other, therefore minus sign will be make sense. Okay, you can see DER. Now I am interested to find out what is this change in the vector, which the change in the position vector, which can be written in units of What are the DER? How do we connect it now? With the d theta is here. Fine. This is the d theta with the e theta. There's the d theta here. DER is this one, is the change in the position unit vector change that is connected to d theta into e theta. Well, this e theta makes sense. It is connected to e theta through the pictures. No? What is the direction in which this is moving? It is in the direction of E. No, this is moving around. This is in the direction of E theta. No? This is what your E theta direction. I'm just going around. This is the direction which is moving. So therefore, this DER of this position vector can be written as d theta e theta. Now we come to this change in unit vector. D theta into ER. D theta into ER. Does it make sense? Yes. This is the DER direction. But this DER and this are opposite direction, therefore minus sign. I am writing this arc length of dE theta in terms of dt, and this direction happens to be, what is this direction? Opposite to that of this. Therefore, there is going to be a minus sign here. This ER is not in this direction has been taken. This is taken in this direction. Therefore, it's going to be ER. Please note that this is the radially which is coming out direction. Okay. That arc length, this arc length and this arc length. Please note down. This is the arc length. This is the arc length. This is the change in the ER. This is change in dE theta. Now you are going to connect it in terms of d theta. Both are d theta, but opposite signs. Either through this or that, you can add it. And then you have a ER vector and E theta vector. So you can see this is the E theta vector direction. This is the ER direction. I think that should be clear to you. Otherwise, you cannot understand this picture. I hope that I made it rather little clear. Is it clear to you? Please note down. Let me explain to you one more time. This is the change in the unit vector. Agree? DER, change in the unit vector. This change in the unit vector can be represented in terms of arc length. This arc length is d theta into this length. This length can be found by using this d theta and the e theta direction in which they are moving. The direction in which is going to move. DER and d theta. Now this is connected to e theta. Similarly, the d theta is d theta in terms of ER direction. This is the ER direction. This is e theta direction. That is what we have used. So DER you have, d theta I have in terms of, and you can see here the directions of R along this, then theta along this. Similarly, you can see the del ER, del E theta. The unit vector changes. This is the unit vector changes, and you connect it to this length. Because this happens to be unit length, you don't have to worry about this modulus of this. Modulus of this gives unit. Okay, so you can see this connect del ER connecting to E theta and del E theta connecting the ER direction. So this and this, they are opposite directions can also be made clear. Okay, I hope you can spend little more time on these pictures and try to have some understanding. Similarly, you can follow the path also and we can explain. P1 to the P2, this arc length ds and then dr, these all can be written in terms of R2 and R1 position vectors. What we have done so far is the given in terms of unit vector, which can also attempted through the position vector. You'll end up with a similar result. So this is what the relation. And if you have too much of difficulty in understanding, better thing is follow this one. Assume that r cap is function of t, phi cap is function of t. That's all. That's what the result that you have. That is what this being written here. Now, with this, you can look at what is happened to the velocity, position vector, velocity or displacement vector, and then you have a velocity vector and acceleration vectors. Okay, I think we are interested now. These are parameters. That's what your dynamics in the polar coordinates. Okay, I think this you have some puzzles to understand. So maybe you think it over, then think it over again, and some more time we will discuss. After doing some more computation with the physical problems, then we will come back and visualize it and try to understand. Then it will be easy for you to understand. See, when you are moving this, no, we are finding DER only with respect to the ER, which is a unit vector. How much is the change in the unit vector that you are changing? Then the what are the change which is taking place with multiply with this scalar quantity, that gives your overall change in the dr vector or the DER vector. Okay, so this is unit vector, and if you want to have actual magnitude, it's something like this. It goes r theta, and when you are moving from the path P1 to P1 to P2. See, this is the path vector now. Okay, you are moving from here to here. So when you analyze this also, you will get similar relations. Okay, similar results will be possible. Similarly, we are taking this theta direction. Okay, this E theta, which is moving down. Okay, it is moving down. Now this movement again connected to this the d theta. So connect them. So now you can see that when you are handling, when you are looking at the d theta variation, it goes in terms of ER. When you go into the DER, it goes to E theta. So here ER and E theta. D theta is just common. Divide both by this small infinitesimal time d theta, then you will get the relation whatever which you have described earlier. Fine, let's go to the determination of the components of the velocities and acceleration. Okay, so now we can see that there is a displacement of r cap vector from position r cap from at the time t1 to t2. Okay, this is r cap we are looking at. So this is the del phi which is involved. This is the time t1 and time t2, and we put it in terms of the vectors now. This is the del phi r cap t1. You can see del r cap at the time t2. So now this is the small change from time t2 t1 plus del p. Then similarly you can find out what is the pi at t1, pi at t2, r1 at r. These are all you are finding the pi t1, pi t2, and then r cap t1, r cap t2. Okay, so these relations are this, and automatically you find this can be replaced by pi cap connecting del r cap is del pi into pi cap. It can be written as pi dot del t. Which implies that I am dividing by del t and multiplying by del t. That's for the relation. Del r is perpendicular to r cap. Del r is perpendicular to r cap. This is another puzzle that's happening. The unit vector change is perpendicular to this. Now dr cap by d theta now is getting converted into the form of a pi dot r cap. Okay, so now we can find that the r equal to r cap with this dr by dt, if you substitute, you'll see r dot derivative can be taken as r dot r cap plus, see what I'm trying to say, this if I take a derivative, because it's varying with time, I'll get r dot as two variables are there. R dot, which means I'm differentiating this, keeping this constant, r dot r cap, plus next one what I'm trying to do is keep the other one r as fixed value and take a derivative of that, dr cap by dt, because it's a function of time. R cap is function of time. Okay, so now you have the connecting relations of dr d theta, and you have r in terms of that, and you can see the dr by dt we already know, and make a substitution, and you end up with this v, which is r dot equal to, you can see here, this first part, time derivative of the position vector with an r cap plus r into pi dot, which is the time derivative of the angle, and then the unit vector, which means there is this one component which enters here. There's another component which enters because of treating them unit vectors as a function of time. That's what it boils down now. Finally, you have a velocity component in which you can see that this r dot is dr and v pi is r pi dot, which is r omega. So what does it mean now? Here I have a derivative of this pi, which gives the angular velocity omega, derivative of the pi, time derivative of the pi, which gives the angular velocity, which we write it as a v pi. So vr suffix r is one data, and it has a direction of r cap. And this has a direction of pi cap. Okay, so now what is the beauty of that? R cap and pi cap must be perpendicular, no? Are they perpendicular or not? They are unit vectors of the polar coordinate. They should be perpendicular, and that can be checked. And how do you check that? We have already r cap and pi cap here. I have an r cap, and I have pi cap already has been found. Take a dot product of that. Check it whether it goes to 0 or not. It should be. It should go to 0. So naturally, you see that velocity components what you have with an r cap and a pi cap, they are going to be perpendicular. So now this is your angular tangential motion. It is something like r pi. What do you get? What is r pi? R into pi. Come on, r pi is the length, no? Hello? You have a position vector magnitude with the pi gives the arc length. What I'm trying this is the arc length that we try to do. For any ds is the arc length. Any path doesn't matter. With a circular, it's circular specific case. Okay. So therefore, you find that this is the length and take a derivative of that with respect to this pi. You have a r and omega is happens to be angular velocity. Therefore, this is v pi, which is tangential to the r vector. R cap. It is true. Now we can visualize that r dot r cap, r pi dot, which is another velocity. One velocity is here, this another velocity is here, and with the vectors of r cap and pi cap, they are mutually perpendicular. It should happen all the time. Okay, that is what the picture is trying to show in terms of the perpendicular relations. Okay, if you are moving along this direction, I have a velocity which is as a component r dot with an r cap, and along this I have r pi dot, which is equal to r omega. That is what this relation says. You get it now? I think v vectors is in this form. Starts from here, it comes out consistently, very easily, starting from this r equal to r with an r cap. Take a derivative. This is the, please note, this is only the unit vector derivative, which we can substitute it back. So when I take this and I am substituting that, okay, this is your pi dot pi cap. I am substituting here. That's all. Okay. I hope this is clear again. Go through them again. Try to digest these relations because they are all very, very important for us. At later stage, when you start learn about this Lagrangian and Hamiltonians, all the places they will be used. Okay, I hope there's some clarity is there at this level now. So please remember only one point. Unit vectors are function of time. That's all. Take care of everything. That will take care of everything. Okay. Right? Fine. So now we find there is a velocity has two components. One is the radial, the tangential. And this omega, it is like a frequency, but it is completely different. Phi dot, which we take, it is a derivative with respect to the angular motion. Okay, there is an angular motion which is involved. It is going around and around. What speed that is going, that is be dictated by your omega. Okay, now we have the V found, and what is to be next level? I want to go to dynamics to the next level. I have to take the time derivative of this. Is that right? That gives the acceleration. We have to do it or not? Because this we have found velocity has been only found. And we need to go ahead with the derivative of the V to get the acceleration in the polar coordinates. Acceleration. Now look at the acceleration. What is going to happen now? And these are all, r cap is a function of time, phi cap is also a function of time. And then when you take the derivative, you have to take the derivative carefully using the product rules. More than one variable is there, then all should be taken into consideration. Okay, let's try to look at that again by taking this v and take a derivative of that with respect to time. Do you find this is what the relation that you are be getting it? Please check whether this is right or not. Look at that. Is this right? There are two products like uv, no? You have u and v. I'm retaining this r cap, take a derivative with respect to r double dat, plus retain the r dat, take a derivative of dr cap by dt. This is over. There are two terms that I'm getting it by taking a derivative of this r part alone. Okay. Now there are three quantities here. 1, 2, 3 of them are. I'm supposed to get 3. Is that right? And it can be grouped with the unit with respect to unit vectors. I have a pi cap. Now you can see that this can be taken a derivative. R dot pi dot pi cap is retained. Next is R pi double dot pi cap is retained. Then you have a R pi dot d pi cap by dt. Is that clear? Derivative component, I have 3 terms here. There are 2 terms you have, because there are product of 1, 2, 3. All the 3 are function of time. Therefore, I have to write like this. And if I take a derivative, I have 3 components, and it is being grouped with the pi cap separately, and then d pi cap by dt. Now you make a substitution for a d r cap by dt already, which you have found. You remember that? What would you get here? dr cap by dt. Already we have found this is dr cap by dt, pi dot pi cap. That would be entering here. Then you have another component, which is d pi cap by dt. That's equal to minus of what? Pi dot. Now that also can be substituted. Once you do that one, I can group them in terms of r cap and the pi cap. I find this is going to be the radial part of this acceleration. This is the angular part of this acceleration. Is that clear? I hope it will be clear for all of you. There should not be any problem here, because we are all familiar with the differentiations. The differentiation is done properly and then made a substitution, and we are ending up with these equations. They are all very easy to realize. So finally, what you have is you have a r cap component is this r double dot minus r pi dot square plus r pi double dot plus 2 r dot and pi dot with the pi cap. What are these 4 4 components that you have. What do they mean? And how are you going to handle that? Okay, it's all very challenging to understand. Of course, this can be represented in terms of angular momentum and the rotational motion, which is V equal to omega cross R. Okay, and then suppose you can see that this omega and the angular momentum component, they are parallel. This is what the situation. They are not parallel, making an angle. Then you can see this angular momentum direction will be changed completely now. Okay, with respect to this omega vector. Please see, note down. When you have a circular motion in a plane, omega, now you please remember that omega, angular momentum are all vector quantities, they are connected to each other. Okay? Do you know omega cross r equal to v, which is a tangential vector, velocity vector. Okay, and r cross p is an angular momentum which is lying along the z axis. And omega and these are in the same axis, and when they are going around in the plane, this is what happening. Okay. Now, suppose the L vector changes the angle or direction with respect to this omega, then you see this is what the thing that's going to happen. Means this is the r cap, r is coming here, and then there is a particular theta that is sitting here, and this L vector and omega vector are not in it. Suppose if you bring down here this plane, you bring it in this xy plane. You know, what happened? Omega and L the same direction, huh? I hope you are able to understand what I'm trying to explain. This plane of rotation, bring it to the xy plane. At that time, omega and L will be parallel. This is what the situation. Is that right? No? It's very easy to read it. I'll show you now. See, this dashed line you have now, right? You bring it down now. This plane, bring it on this xy plane, this dash one. Then this comes and sit on this plane now. At that time, omega and L are parallel. You are bringing this down. This blue comes down straight. This R is going to be sitting on this plane. Okay. Please note down. This is very important for us to understand. Okay. Your concept of all magnetic moments, all will be connected to these things. You look at this. This blue dot, which is sitting on this xy plane with the radius r, is getting lifted up, which means that L is no longer parallel to this. It's making an angle theta. Okay. So now we can see that what is going to happen in pure dynamics. Okay, it's very interesting dynamics that's going to emerge by this when finite theta is involved. So you can see that this is in a plane along this xy with a fixed r, and this is no longer same. It is going up, and of course r can be changeable. You can change it also, or it can fix it also. So now we can see what happens if r is changed, r is fixed. Now you can see there are 4 components are there, and two components for each one of the along with the unit vectors, and we try to understand them. And you look at in terms of r vectors, and this is the p vector. And of course, we will write it as an f. For a f vector implies that's going to be an f for r cap, f by pi cap. And b vector is an r cap and a pi cap. Right? You can see things are very comfortable now by writing it as an f r and f pi. And r component is this, and this is the pi component. Okay. Now you look at this equation. When r becomes constant, what will happen? Fr and f pi. Yeah, that's right. Here and again pi dot it goes to 0, and remaining is available. And that's what your description of a in a plane, a fixed value of r. That's what your dynamics. Corresponding velocity also can be found. That is what we are talking all the time about the circular motion with a fixed value of r. And what are the forces involved? What are the velocities that is involved? That can also be understandable by just by looking at these equations, which we have found already by taking a proper derivative, assuming that r cap and theta cap is a function of time over. That's what the total concept which we need to understand. Now look at all the terms and try to understand. See, the mr double dot term is quite intuitive. For a radial motion, it simply states that f is equal to ma along the radial direction. Is there any difficulty in understanding this? Mass into acceleration. That's what your m into r double dot. Okay? First term is clear. Is that right? Okay, come to the second one. mr double dot is double t dot. mr double dot, phi double dot, or theta dot, doesn't matter. That's not an issue at all. mr phi double dot. Okay, or a theta double dot, doesn't matter. Term is also quite intuitive. For circular motion, it states that f is equal to ma along the tangential direction, because r theta double dot is the second derivative of this r theta along the circumference. You have a length along the circumference. Take a derivative twice with respect to theta. That is what your r double theta. This is also equivalent to f is equal to ma. This is the whole thing is a length now. Then you do this theta component, you take a theta alone, that you have a theta double dot. It is equivalent to length derivative, second derivative. Therefore, it is also equivalent to f is equal to ma. Is that clear for all of you? I have a length r theta. Okay, two derivatives I have taken with respect to theta. That's r theta double dot or a pi double dot. So now this is an acceleration, which is equivalent to ma, the second derivative of a distance along the circumference. That's what it means. This is in the tangential direction. That's what your acceleration. Clear? Look at what is this. This is the length. Okay, and then this length is along the tangential. That's why you have an r theta. So it is a tangential acceleration. So that's what you have. Come to the other terms now. Minus r mr theta dot square. Them also fairly clear. The circular motion, it says that the radial force is m r theta dot whole square divided by r, which is equal to mv square by r. So this is another way to look at things, which is familiar force that causes the centripetal acceleration v square by r. Some problem has been given to refer it. So alternatively, the derivation of this v square by r is a result. Okay? Is it clear now? This is the centripetal acceleration. So now you can see this 4 component of acceleration one by one we are seeing. Now there are two more r dot and pi dot or a theta dot. They are all again the square of this. There are 2 dots are there. So 2m r dot theta dot term isn't so obvious. This is not so obvious. It's not obvious. Okay. This is associated with the Coriolis force. There are various ways to look at this term. One is that exists in order to keep angular momentum conserved. We'll have a great deal to say about this chapter 10. Okay, we are also going to learn little more on this Coriolis force after some time. So this is the Coriolis term. So this is also like an acceleration. Okay. So this takes care of one is that it exists in order to keep angular momentum conserved. Otherwise, it's going to be a problem. We will have a great deal of learning this also. Let us time. So we have 4 acceleration terms. Each one can be understandable by looking at each one of them carefully. Then try to analyze them. Now, as I said, we have r cap and theta cap. If I treat them like time dependent, I have the complete understanding of the velocity and acceleration of the polar coordinate systems. I'm going to directly take position vectors in which the caps are represented by R is a function of time. This is the so-called the vector, which is a function of time. Okay, so let us try to look at this. R of t, which we write it. See, I am taking the pi is also a function of time. Please note. Is it not? I'm writing pi is a function of time. R is also one. Whereas when you use the Cartesian coordinate system, we don't treat like this. Okay. For example, velocity, when you write x component, y component, position vector x component, y component, we don't write that pi is a function of t. But here you have to write because it's varying when the time changes. Now this is the position vector. You write it as a components like this. Okay, in a polar coordinates, we have only the x, r, and cap, r cap and theta cap. Now you take a position vector here, take a derivative with respect to t. Okay, when I do that, you can see r prime of t will be there, cos. Then this will be retained, derivative has been taken here, and we have pi prime of t. That you will be getting it. Similarly, the other one, you can see that's a component sine pi of t has been retained and derivative of this has been taken. Then this is differentiated. That sine component is differentiated. At that time, pi prime of t has been taken. We have taken the derivative of that. So we started with the position vector and we found the velocity is this one. This is what your velocity component in the polar coordinates. Okay. Now, acceleration, how do you find out? T comma 2, d of r, take a derivative twice. And you can see the number of terms that you have, which means there will be two components from here, two components from here, 2 or 3, r of r prime of t. So you can see this. This is what your total terms that you have. When you take a derivative of r of t with respect to t 2 times, this is what you will be getting it. So now you know the unit vectors in terms of pi of t, in terms of cos and sine, because this is an r vector which you write x and y, and we are having this cos theta or cos pi, sine pi, which is a function of time. This is your ru, and this is your pi u unit vector, which we have already seen, connecting the x and y caps, connecting the ru and pi u. I have written same thing. I have not done anything great here. This is what your unit vector. Now, if I take a dot product of v comma ru, I'll get an r prime of t. Okay, this is multiplied by a v dot ru. Similarly, v dot pi u gives r of t pi prime of t, which is already available for me as a velocity component. Multiply with this unit vectors here, and simplification gives the radial component and the angular component of the velocity. This is what already we have found. Is it not? R prime is available. You can see here. That is your R prime velocity. See? This is R prime. Cap, this is r theta, r component, r unit vector, and then r pi dot along the pi. That is what the result I have for the pi. So by multiplying a vector with this unit vectors, I am able to get this pi r theta along the direction of ru. Similarly, pi u direction, this is what the result. Next is take the acceleration, multiply with ru. I'm getting this, and a into pi u, I'm getting this relation, and this is what the components, and this is what the component, which is same as what has been observed with the steps which I have followed here. So the entire things fall in place when I put it in the form of a position vector where function of time, when I add it and take a derivative to y's with the unit vectors of ru and pi u, I'm getting the acceleration component. And then you have velocity, displacement, then you have the velocity components and acceleration component also possible for us to find. So absolutely no problem for us to evaluate all of them. So now if you suppose if you make a circular motion with a fixed radius, you make r is independent of t because magnitude of r is fixed. Only this is varying. And if I do that, usual circular motion results that you will end up automatically. Okay, when r is fixed, it's independent of time. You understand what I'm saying? Here I have written r is a function of t, whereas here r is independent of t, but this pi dependence will take care of that, and I would get the results which usually what you see in terms of the circular motion, the existence of the components. For example, this is what your velocity component. You find that r pi prime of t, which is pi dot of t, and this you have an r dot that goes to 0. Similarly here, that the r components dots derivative part goes as disappears, and you have only this two components which is existing. Okay, which you can get it by fixing your r value here. This goes to 0. This also goes to 0. This I'm getting it. This is also available. That's what the result which I have found. Okay, you can cross check it. This is quite fantastic to see. Okay, when I am fixing the radius and then doing an operation, and I have a complete result what I have here, which is nothing but the special case of this r of t, in which t dependence has been taken out. That's all. Okay, now it seems that all whatever has been studied, it seems to be very simple, starting from here, and whatever you have visualized the pictures and the simple algebraic simplification is available through the simple position vector. Somebody also asked what will happen to the position vectors. That also treated as a function of time. That's all. This has a r cap here. That r cap is also a function of time, and this is have a pi cap, and that's also a function of time. That's what is being incorporated here. This is the component. This is one component. This is another component, the plane of rotation, where r is also a function of time. Pi is also a function of time. That's what it means. This is your actual position vector to solve in terms of sine and cosine, and the sine and cosine part also function of time, position also function of time. That's all. Yeah, you can go through them, spend your time, digest all these things, whatever I have explained to you. And once you have this picture clear to you, then very easy for you to understand the polar coordinates and also spherical coordinates.
So for this, we want to have textbooks which we have to follow. Then we can write it out, and we can do that simplification.
But these are all available in the textbooks, basic textbooks which are all described. These are all whatever I described. They are all available in the basic textbooks. Even these things also very nicely described. If you found, I can give you the references. You can refer them. All the references are available.
Yes, sir.
Okay. These are all well-known, well-established facts in the polar coordinate systems. When you talk about rotational dynamics, okay, you know, linear motion so far we have learned. Now you have a rotational dynamics. Once you start the rotational dynamics, you need to have these pictures clearly. See, once you have this picture, for example, this 1, 2, 3, this is position vector we know, okay, in terms of r cap. And if you have this clear picture about what is this actually, how do we arrive this one?
So since we are not using it often, if we work it out and see, then we may know how this
Yes.
expressions have been used.
Yes, it should be. You have to work it out. You have to work it out. Otherwise, how do you understand the hydrogen atom now?
Yeah.
Okay, it's a physical coordinate system. Okay, in which you need to take about the r, theta, and phi. Okay, and you have an angular momentum. When you talk about, you have a phi component, and you have Lx, Ly, Lz. Okay, all this will come there automatically.
Yes,
They're all available there. So it forms a base for many things which you are going to do in an advanced level. It really forms a base. And once you have this base clearly, then when you look at this equation, immediately you get an idea, oh, this has come from such equations.
Yeah.
So that is what the aim of our study here. Now we can see dynamics is playing a role even on the unit vectors, which gives completely different kind of a dynamics. Is it not?
Yes, sir.
This is completely different kind of a dynamics. Whatever which you have an x, y, x cap, y cap, z cap is completely different here. You can see several things which is enters, and you can see this, we have converted in the form of vector. Omega r omega, what I have written here, no?
Yeah,
Is the
omega bar cross r bar.
Yeah, this is what omega v equal to omega cross r. That's what really going on. And r cross p, this is also available. This is r and cross p. This is the multiply with m, and this become mv.
Yeah, angular momentum.
So therefore you can see r cross p, which is perpendicular to this. So this and this is sitting in the plane. Angular momentum is perpendicular to this. Direction is fantastic now. You can see r is here, and you have the velocity moment here,
Yes,
and multiply with the mass of that. R cross p is your angular momentum, which is perpendicular to this and this, right?
yes.
And what about omega cross r? Please look at the directions of here. What is the direction of v? See, this and this. You see, omega here, r here, and v is some perpendicular that. Please note down. It's very important for us to understand how the tangent. He is asked about how the tangential motion comes. He has asked that. You see, omega cross r, which is perpendicular to this r vector and omega vector. That's why you have omega cross r. Correct?
Yes.
When I say omega cross r, v must be perpendicular to these two vectors. Correct?
Yes, sir.
And it should happen every instant of time.
As it moves around.
Correct? Now, every instant of time. When this is going around, it should happen. So that's why this is a tangential velocity, which is connected to the angular velocity omega in terms of a cross product. So cross products of this and cross product of this r makes sense when you look at immediately by in terms of this r and v. Okay, omega of course we know already. And what happened? This omega and r connecting v is very strange. This is sitting here, this is sitting here. All the time when that plane, that omega r plane moves around, and v will be perpendicular. That is what your tangential velocity. That's why this is the tangential motion. Okay, so it's so nicely it emerges now, and that's why I said if this is going up r, it's making an angle with respect to theta. Then this is what your direction of this r vector. And once that happens, then omega is no longer perpendicular to this, which means omega is making an angle
Theta.
with L. That's the technique, theta. Okay. So these are things that happens when you look at these equations carefully. It's really marvelous to see the things how this get connected to each other. Okay, and in this we have a conservation of momentum and conservation of energy.
Yeah.
All are consistently going. And then the interesting, very many interesting results are observed when they are not conserved also. Okay, then one has to really use the numerical techniques and the results. Okay, so I hope that is. So we'll do one thing. I'll send you these things. Go through them carefully, and give some references also. And that reference also you can refer it, and see that you are able to understand and then get some ideas about this polar coordinates. And we try to work out few problems. So, okay.
Yes.
Yeah. I can stop here now. Yeah, I send it now, both the morning session and this also. Okay.
Yes, sir.
Right, I'll stop it here and we'll meet in the tomorrow's class sometime. And students will be there. Okay,
Okay, sir. Thank you, sir.
thank you.